The next calculus. Here we have a picture of Newton. He is refracting AF. That white light's coming in. It's a whole rainbow. We got a telescope. We got the apple that fell on his head. It's a whole life, but we've got something even better. That contains that old calculus within it and extends it to include a metaphysical tool, and that is the CTMU hological calculus. First off, huge respect to you for clicking on this video. That shows how motivated and intelligent you are to click on something that sounds harder than calculus, the next calculus, and then actually be interested in watching that. That is just incredible. You could be watching your Baby Shark edits or your Sigma male content, but instead you chose to listen to me, and that is enormous respect to you. Fist bump right there. That just shows how much you are focusing your attention and action on that self-education, self-improvement. Just God bless you, man. And my promise is that when you're done with this, you will know more mathematics than any PhD student or professor in the world. And that doesn't mean that you'll actually know more than them, but there are certain things they know that just ain't so. They think they know it, but they're wrong. And you will be right about things that they are wrong about. So you'll get a clear and consistent picture of mathematics. I'm Tommy, and CTMU Singularity is where the power of an individual meets a mindset of absolute truth. I help young guys get so self-actualized that they start figuring out the meaning of the universe. Subscribe right now if you want this kind of stuff in your YouTube feed. And yeah, if this is the sort of thing that you're interested, I think that it would be very good investment of your time to have this pop up instead of your Kendrick Lamar updates. Learn what school won't teach you. And yeah, so the big question for today is, if n equals 1 over 0, does n equal infinity? A lot of people just have this kind of aesthetic reaction of it's either no or yes. Is 1 over 0 infinity? I don't know. It's really hard to say. But it's not as logically clear as some people make it out to be. And usually this has gotten around by just saying it's undefined. But that's no fun. We want to actually define things. And if it has if it can be expressed like this, it is actually able to be well defined. So we can invent a number such that n equals 1 over 0, just as I equals the square root of -1. Langan says this number already exists in the form of infinity. However, there is a cheat involved. 0 becomes the infinitesimal 1 over infinity, which is of measure 0 in the real unit interval. That is, 0 is interpreted as a measure rather than a quantity, and a non-zero infinitesimal entity is invented which coincides with measure 0. This can be expressed as follows. An infinitesimal is a non-zero number that is less than any finite quantity, and is therefore quantitatively negligible, but as sub-finite measure 0. It's quite a trick. Quantity has been disjoined from measure using the term infinitesimal, and then crudely plastered back together with measure using the phrase measure 0. An infinitesimal is a non-zero quantity representing zero progress along a line segment. The cost is that infinity breaks finite algebra, requiring that the rules be changed as prescribed by Cantor and others. It is on the strength of this cheat that the infinitesimal calculus exists. For over a century, this has been officially rationalized to high school and college students using infinite converging series and the Cauchy-Weierstrass epsilon delta technique. But on close examination, Langan says, this fails to provide a satisfactory explanation for either infinitesimals or the calculus. Although 1 divided by 0 is usually said to equal infinity, that would mean that if you multiply both sides by 0 and then divide by infinity, that would be functionally equivalent to saying that 1 divided by infinity equals 0, which is a very nebulous proposition. This means that it takes a non-terminal infinitary process to stitch the numbered line back together from that 1 over 0 to a finite interval. And this is justified in calculus using the idea of infinitesimals and the admittedly difficult idea of a sub-finite measure 0. Basically, if you quantize a number in terms of zero-dimensional cuts, you'll be shocked when you take the integral, the area under a curve, which in principle consists of all and only these cuts, and have a definite area at the end. Therefore, all integrals are actually the sum of discretely quantized area representing a sub-finite but not zero measure 0. So he says a non-zero measure 0. And we can show this. Here is a little video that will show basically what we're talking about when we when we look at this epsilon delta formalism. So here we can see we are, as we converge in on a point, we are gradually lowering the how much we are allowing the change in the function to happen along the y-axis with the epsilon, and how much the change in the function is happening along the x-axis. And once we get this to almost zero, as both of them converge along that point, we just say, oh, well, when it gets to zero, that is the limit. But the problem is, it's a non-terminal process. It never got to zero. It didn't even get close to zero in this freaking animation. And so that's a big problem for understanding, all right, these things with continuity, is that it basically requires that we give up our reason and just say that these zero-dimensional cuts actually have some finite extent, or just ignore it entirely, as most mathematicians do. And so this is usually justified using that epsilon delta formalism, which describes a limit as closing in on a point from all sides, using a recursive infinitary function that converges on the limiting value. However, this is not so much explanatory as descriptive. We're still left wondering, what is the infinitesimal, and how does the calculus of continuous change, or the sum of the area under the curve, add up to any definite value in the coordinate plane if the coordinate plane has infinite points of zero extent? We would think 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0, it's 0. So when do we get from 0 to a finite number? When we take the area under a curve. Do you see the problem here? So further, where 0 is a limiting algebraic representation of unbound telesis in human cognitive perceptual syntax, a veritable and irreducible mental coupling of nothing and something in human cognitive perceptual syntax, the entire coordinate space, in order to make sense of infinitesimal calculus, must be embedded within the algebraic system of the self-configuring self-processing language SCSPL, injecting the definition of zero-dimensional cuts with non-terminal extent that it operated on by the measure of area. Notice how this fits with Russell's definition of numbers. A real number is a segment of the series of ratios in order of magnitude. An irrational number is a segment of the series of ratios which has no boundary. A rational real number is a segment of the series of ratios which has a boundary. An irrational number like the square root of 2, which equals roughly like 1.414, but has infinitely many digits in its decimal expansion, has no boundary, because you cannot pick a value infinitesimally smaller than it and infinitesimally greater it, meaning you can't converge on it from both sides. This is an operation called a Dedekind cut, because it creates a zero-dimensional cut in the manifold for any segment with a boundary. Because the square root of 2 is not a definite value, it has no boundary like other real numbers. So that means it doesn't even appear on the number line technically, unless you were to terminate it at some digit, and then it wouldn't be the square root of 2. It would be like the square root of almost 2. Yet the real number line must include somehow both, not only traversing finite measures of area, but also subfinite infinitesimals that have no intrinsic boundary. To overcome this difficulty, we require the calculus alluded to in a previous presentation that quantized the manifold in terms of syntactic operators rather than zero-dimensional Dedekind cuts, and therefore gives all values in an actual boundary, a syntactic covering, and the containment of one syntax by another that can be operated on by the global syntax of a function. So because we are including all of the points within the manifold as part of the structure and dynamics of the coordinate space itself, we give this kind of covering wherein everything has this intrinsic boundary defined by the syntax, the rules, and structure of the entire mathematical space. Thus, in conspansive calculus, when we take the integral of a function, trying to find the area from 0 to 1, all of the points in between those values are operated upon by the integral itself. The integral transforms the modeled space to take up a definite area, which does not take up existing as pure potentiality. In standard coordinate space, area is not conditional on the function being modeled. In conspansive calculus, however, the function itself is generated in coupling with its area and embedding mathematical space. There is no fixed plane out there, so to speak, externally to the function, but only when the function is actually modeled by the space. So the function and the space emerge in coupling with one another. We only care about the specific value of any given point when we desire to find the value at that point. We should be careful to say that the value has zero extent, but rather that it's zero potential extent that can be measured by a finite interval. Or actually, that it has potential extent, rather, that can be measured by a finite interval. I think this is probably how we'll start to think about conspansive calculus, at least in its elementary formulation. I'm still sort of taking a stab in the dark, right? Seeing as Langen's papers on this topic have yet to be published, so I haven't read them yet. The idea of an irrational number goes a long way towards that idea, consisting of a set and one or more operations on that set. Therefore, a number must be defined in terms of an algebraic system, or else it would be impossible to provide syntactic covering to the embedment of the syntax of the arithmetical function within the broader algebraic system for a fraction like 47 over 49, which has an infinite non-terminal decimal expansion. Bertrand Russell writes, it is easy to prove that the series of segments of any series is Dedekindian. Given any set of segments, their boundaries will be their logical sum, i.e. the class of all those terms that belong to at least one segment of the set. However, this is not good enough because Dedekindian cuts do not have any syntactic covering, the embedment of the syntax within the zero-dimensional point within the syntax of the coordinate space as a whole. So for that syntactic covering, you need to have this dual self-containment, wherein the rules and structure actually resides within every point within the mathematical space and vice versa, which supposedly consists of all and only these points. So there's no way that together these points can form this space and have this kind of operator algebra that has when they have zero extent when added together in mass. So they need to have a definite extent, and therefore these naked zeros aren't going to cut it. They have to actually be clothed zeros with the syntactic covering. Only when you treat infinitesimals as syntactic operators, as things which are actually transforming the global syntax of the mathematical space, can you have any meaningful formulation of calculus. The continuous number line of zero-dimensional Dedekindian cuts is absurd on its face, and although assumed by most mathematicians for convenience, the so-called continuum hypothesis has yet to actually be proven mathematically. The reason why conspansive calculus is sometimes called hological calculus is because its mathematical space expresses the property of hology, where the syntax of the entire space is topologically embedded within every part and aspect of the algebraic system. The reason why syntactic operators differ from Dedekindian cuts is because the entire coordinate space provides syntactic covering for their objects, properties, and relations, allowing them to cohere to model the space. In the CTMU, a syntactic operator is also called a noyon, the basic quanta of mind, the fundamental entity in SCSBL, a quantum of infocognition, self-transducing information, or a fermion, quantum identities capable of mutual interaction, such as electrons, protons, neutrons, and all neutral atoms with an odd number of electrons. So it's a noyon and it's a fermion, and it's a coupling of those two aspects of both that mental and physical aspect, and all syntactic operators contain both of those. So therefore, the idea of a syntactic operator in conspansive calculus to model them is also necessary in order to meaningfully express mental dynamics using metamathematical notation. The CTMU meta-language, infocognitive teleology, information processing and transduction, and even probably quantum mechanical systems. Without this new kind of mathematical notations, these disparate fields will forever remain in the dark ages of the linear ectomorphic semi-model of math and science, rather than fusing this identity with the enlightened conspansive semi-model, as the CTMU suggests. The conspansive calculus simply notates this shift and discerns its implications. The hological aspect of this calculus is embodied through a process called distributive morphism, whereby a structure-preserving topological mapping exists between the levels of the manifold, injecting the identity into each of its embedded points in the mathematical space. Langen says with respect to this isomorphism between the global space and each syntactic operator, that one needs to be very clear on the level of identity to which any given statement or mathematical symbol refers, and two, one needs to allow for the distributed nature of certain morphisms, whereby distributed we mean that the morphism applies to each point in a topological point set. These two guidelines require that the modeled space be injected into each point without any loss of structure or coherence, which is not possible within ordinary topological space. This new form of topology, the study of spatial relations, requires a self-dual formulation that dissolves the dualism, as previously herein discussed, between the coordinate space and the modeled function. Notice the implication, Langen continues. The use of distributed morphisms implies that each point of any topological space subject to distributed morphism has internal structure. In the CTMU, this internal structure is called syntax. Hence, the points are called syntactic operators. The points that are modeled and have this self-dual feature that can operate on the global property of the system, be they mental, informational, physical, quantum, or mathematical, are syntactic operators because they transform the global identity of a meta-language while preserving its generic properties, affecting functional coherence within the modeled system and all of its elements. Langen says, here referring to human beings, that some syntactic operators cannot support full isomorphism to the global identity. Hence, they're subject to syntactic restriction, and isomorphism is limited to some proper part or aspect of the global syntax. But points in which the syntax of the global identity is fully imaged are not restricted in this way. It follows that their syntax is isomorphic to global syntax. This does not imply isomorphism with respect to external state. Yet, with respect to a generative coordinate space, the points are all saints, so to speak. They're perfectly in line with the global identity, with the identity of the mathematical space, and never deviate from its dynamical features. Therefore, comprehensive calculus can be defined as the best of all possible mathematical universes, containing objects capable of mutual interaction through the manifold itself. This means that information processing can be modeled metacybernetically in conspansive coordinate space, with the information being beamed using the syntactic covering of each syntactic operator within the global syntax of the mathematical space. This descriptively contained syntax allows for the operators to inform the global space, just as the global space reconfigures the points according to the modeled function. Conspansive calculus is to mathematics just as relativity was to physics, modeling a topological system in which the space tells syntactic operators how to move, and syntactic operators tell the space how to curve, thereby allowing the space to model complex dynamical systems that are possible within the formalisms of standard mathematics. As such, it represents at least as great a stature in mathematical history as Descartes' analytic geometry and Newton and Leibniz's calculus, alone justifying Langen's place among mathematics' historical titans. Thank you. Let the light shine forth in the darkness. May the peace of our Father in heaven be upon you. Like and subscribe. Peace.